Today's goal, we're going to finish up the gerrymander problem that we started in class last time. And today we're going to introduce a new technique for creating efficient algorithms. This is the greedy algorithmic technique. It's often the first thing you think of, but it's the most subtle and complicated to prove correct. We're going to start with some simple examples, a scheduling problem, and then a cache memory problem. Both can be solved with the greedy algorithm. And then on Thursday's class, we'll consider more complicated examples of greedy algorithms. For example, Huffman coding, which is a compression technique. All right. Recall the problem from Thursday. We're political operatives. We know we have to divide a state into districts. Each of the districts consists of precincts. We want to stack the division so that our party will win in both districts. I gave an example on Thursday where you can imagine 4 precincts, and depending on how you paired those precincts together, in one situation, one party won both precincts, had a majority in both districts, and in another situation, it was 1 and 1. So we're taking a simplification of this problem. We're assuming that we have a set of precincts. Each precinct has the same number of people, and each precinct has A, people that vote for one party, and B, people that vote for the other, and AI plus BI is always going to be the same constant, the same number of people per district. So this was our problem. We were given M. We are given M, the number of people per precinct, and we are given A1 through AN, which is the proportion of people that vote for party A in each of those N precincts, and N is even in this case. And we have to output 2 districts, and the following has to be true. The size of each district has to be the same, i.e., same number of precincts. And we would like it that the number of people that vote for party A in District 1 is a majority. The district needs to be such that party A has a majority in both of the districts. And that majority condition is represented by this numerical inequality, i.e., the total number of people divided by 4. Since half of the precincts are in the district, and half of the people in that district will vote for A, at least half. And of course, if no such solution is possible, we output that our job as political operative is a total failure. Now, if you remember from Thursday's class, 2 important slides. The first slide was we looked at the state of the world before that very last precinct had been assigned. So in that very last step, D1 had K precincts assigned to it in X votes, and D2 had N minus 1 minus K precincts in Y votes. And when we assign a precinct to a district, one of 2 things happens. Either the state of the world changes to the blue state up there or the red state up here. We use the insight from what happens when you assign a precinct to one precinct or the other to help us define this variable right here. Sjkx, it's going to be a true or false variable, and it will be true if there exists an assignment of the first J precincts such that the size of D1 is equal to K, and the number of people that vote for D1 in District 1 is X, and the number in District 2 is Y. Right? Which is essentially what I wrote right there. And then came the punchline of the problem, which we discussed very last part of last lecture, which is that this variable, it's going to be true in one of 2 ways. Either you can assign J minus 1 precincts to District 1 such that you can assign J minus 1 precincts such that D1 has K minus 1 precincts. You assign this last precinct to D1, in which case there are X plus AJ votes, or, in other words, this jth precinct has to be assigned to either District 1 or District 2. When it's assigned to District 1 and this condition is true, then this will be true. If it's assigned to District 2 and this condition is true, then this will also be true. So with that simple equation right here, with this equation, we can now come up with an algorithm for this problem. It's going to be a series of nested for loops as follows. So the first step is going to be to compute this very large matrix, and then we're going to inspect elements of this matrix for any variable that assigns all n precincts, such that District 1 has n over 2 precincts, such that x and y are both greater than mn over 4. If any of those conditions are true, then we know that there's a way to gerrymander the districts. Questions? From that, how do you find the assignment? So this is a generic technique, the backtracking technique that we've always used in class. So what we would do is that in addition to keeping this variable s, at every variable we'll also keep the, whether the district, you can basically create a choice variable that's going to be District 1 or 2. So at every variable, if S is true, then it basically explains how that jth precinct was either assigned to 1 or 2. Whichever, if this made the equation true, then it's 1. If this made it true, then it's 2. And then you just follow those back. Question? Absolutely. The logic behind this equation. Okay. So this variable stands for there's a way to assign j precincts so that the first district has k of them, and x people vote for A and D1, and y people vote for A and D2. This is going to be true if there was a way to assign j minus 1 precincts such that D1 had k minus 1 of them, and then you assign that jth precinct, AJ, you assign it to D1, which makes this j minus 1 go to k, and makes this x minus AJ people who previously voted for party A and D1, now x minus AJ plus AJ, so you get x people voting for A and D1. And before you had y people voting for A and D2, and that doesn't change. So this is one way for you to set for this variable to be true. The other way for it to be true is that you assign that last precinct J, you assign it to District 2. In which case, for this to be true, you had to have k people in D1 already, x people already had to vote for D1, for A and D1, and then this many people had to vote for A and D2. So this is exactly the same logic behind the staircase situation. Right? Was it possible to get to that top stair? You could only have either taken one step or two steps. In this case, the only way for this variable to be true is one of these variables had to be true. The only difference, the only mind-warping aspect of this problem is that it has so many dimensions to it. So, very good question. The brute force, I say, would be more than x to the 4th. Because you have n precincts, and you have to look at every combination of n over 2 of them. So brute force would actually be n choose n over 2, which is, you have to consider every subset, or actually, this is going to be 2 to the n over 2. Because the number of, you have, essentially you can look at the assignment as a binary, as a binary number, And a 1 is whether you assign the precinct to District 1 or District 2. And so the number of assignments, that you have to look at is going to be 2 to the n over 2. You have to look at all binary vectors in which there are n over 2 ones. The question you asked is, how fast is this algorithm? And so let's compute that. This loop is going to run n times, right? This is a nested loop that's going to run n times as well. Notice that it only goes to n over 2 because we only need to look at the last value that we ever need to actually look at is n over 2, right? This is basically going to... Okay, so if we put all of these together, we get something that's 1, 2, 3, 4, n to the 4th times m squared. So it's not a fast algorithm, because if we have 100 precincts, already n to the 4th is a pretty big number. And if you have 100,000 people in a precinct, that's a big number as well. Question? Yes. So the question is this condition. Why? Because District 1 is going to have n over 2 precincts in it, right? So that implies the number of people in District 1 is going to be m times n over 2. And that means that majority in District 1 is going to be n times n over, at least m times n over 4. Does that make sense? Right? There are n precincts, A1 through AN. Half of them have to be in District 1, so that means that there are m times n over 2 people in District 1. And so then this is what a majority means. More questions about this? So there is a problem. Yes? What? This right here? Good question. This is the number of people that vote for A in District I. So AI is the number of people that vote for Party A in Precinct I. So if you look at this picture, right here, A4 is the number of people that are going to vote for candidate A in Precinct 4. So an algorithm of this form, you'll have homework 3 requires you to come up with an algorithm of this form. Question? Yeah, P just stands for precinct. So there's precinct 1, precinct 2, precinct... yeah, it'll be the same as M. Yeah, technically this P is redundant. It's saying there are N precincts, and each precinct has AI votes in that precinct. In this version of the problem, you don't need the P. You could imagine a version of the problem in which the precincts don't have the same number of people. Yeah. Very good question. So the question, let me repeat it for the audio. The question is, why do we have to be so precise about this quantity? Because in the end, all we care about is whether there's a majority. So why not define this variable so that it's true if there are at least this many people? Let's ask that question. It's a very insightful question. It's a question that really tests the understanding of this algorithm. Why does this variable have to be defined as there are exactly this many people? Exactly X people. Why exactly X? Well, he's suggesting that let's redefine this variable so that it says there exists a split of the first J such that k are in D1, such that at least x people. The suggestion is let's change it so that at least x people vote for party A, not exactly x. Perfect. So, because it's written as exactly x, so that because this variable is defined as exactly x, that means that our update only requires 2 checks. If what you suggest is that we say that this is a greater than or equal to, right? Then we have to, first of all, when this is true, we actually have to update everything below it, right? If this x was true at this spot, then we'd have to update x minus 1, x minus 2, x minus 3, right? Because at least x minus 1 would vote. If x are going to vote, then at least x minus 1 would vote. So at every step of this operation, just updating this variable would take order x time. Moreover, you'd have to check more than 2 spots. Right? Because if x minus aj, or x minus aj plus 1, or x minus aj plus 2, etc. So this the right-hand side would be more complex, and the left-hand side would be more complex. So it's key for this thing to define the problem so that you have a lot of variables that are precise, easy to update, and then later on, you can go in this step right here and check. I didn't exactly mention the time complexity here, but you can sort of see that this is going to be order n squared, m squared right here. Anytime you have to split teams into 2 or split some set so that it satisfies some property, hint, hint, this is the type of approach we look at. Question? I'm going to answer your question in 2 ways. The easiest to see generalization of this for 3 districts or 4 districts is just to change this variable and add a few more dimensions. You can see how to do that, right? You'll have j, k, l, m, n, o, and then x, y, z, etc. So you can just expand that in that way. Now, turns out later in this class, we're going to talk about some more advanced dynamic programming techniques. So when situations occur like this, where this is too big, there's some other tricks you can play to try to... Initial dynamic programming solutions might be this big, but you can look at them in a different way and try to reduce them. So there's some other advanced techniques. The problem you're thinking about is like a partition type problem. It's generally, just like this one, going to be an NP-complete problem. And so we don't expect efficient algorithms for them anyway. This one is sort of a trick. I'm calling it efficient because for small values of n and small values of m, it's actually feasible. More questions? I'm looking for you to extend this type of approach to this idea that you're going to have a true or false variable here and use that as your dynamic programming solution for the homework. Our next topic. So as you know by now, I start new topics with simple examples of problems and get to more and more complicated ones. Like we did with dynamic programming. We started with staircase, log cutter, matrix chain multiplication, typesetting, seam carving, gerrymandering. The new technique we're going to introduce now is the greedy technique. We're going to look at situations when we know that the greedy technique will actually work. It's often our first instinct to make those local optimization steps and hope that things work out. But it turns out that they only work out in some very special situations. And you should have the techniques for determining when those situations occur and convincing other people that your solution is actually going to work. Your greedy solution, which is the natural, intuitive one, is actually going to work in this situation. So let's consider an example. This is called a scheduling problem. So this room, for example, it's a hot commodity. It's one of the best teaching rooms. And imagine that we have a bunch of classes that we need to schedule. To make maximum utilization of this room, we'd like to put as many classes in this room as possible. So let's imagine the list of classes include a starting time and an ending time. And as much as it might seem feasible, like, for example, we have 2 projectors, so it does seem feasible that we could have one class over here and another class over there, maybe. If you get bored of this one, you could wander to that one. Maybe it's something you should suggest to the dean. I'm not sure. But, but for now, let's assume that only one class per room at the same time. There could also be a quantum argument that you could have 2 classes at the same time, and you could basically have 2 lectures at the same time. But let's assume that one class per room per time is the de facto standard. I know a lot of you are also probably on MOOCs at the same time in this class, so already there's this precedent for doing more than one thing at once. So the problem is you're given a schedule with constraints, start time and end time. You can only do one thing at once, and you want to do as many things as you can. So to formalize that, we have the input is going to be a list of activities. These activities are just names, for example. These activities are just names, like this would be the name. And each activity has a start time and a finish time. And although I know that you would love to have classes that end before they start, in this situation, every class is going to start before it ends. And the goal is to find the largest subset of compatible activities. So the goal is to find some subset of activities such that for any two activities in your set, the finish time of I has to be less than the start time of J. But better, there we go. Put that up. A better way of representing this type of problem is with a diagram like this. So by the way, we can assume that our input comes in sorted order by finish times. So just like this diagram, the finish times, F1 finishes before F2, finishes before F3, all the way up to Fn. And the start times are essentially represented by these dots right here. So that's essentially the problem. You're given a list of classes, and you can't have any 2 classes overlap. So you need to find a maximal set that doesn't overlap. Now we can solve this problem with dynamic programming. In fact, why don't you let me give you one little extra hint. So we're going to solve this, first we're going to solve it with dynamic programming, and then we're going to show how the easier solution, a greedy solution, also works. So the dynamic programming solution, let's go ahead and for each of these activities, let's project these down onto a line, okay? E1 is the first event. E2n is the last event. Right? So events are either a class began or a class ended, and we use E essentially to denote when class begins. And now the best M is basically going to be the most number of classes that can be scheduled between event 0 and event M. So, since it's a most, we know that the dynamic programming solution is going to involve a max. Spend 2 minutes with your neighbor trying to figure out how the DP solution here works. Let's say that last class is part of your solution. And then what does it mean? Your best solution is going to be 1, because it's that last class, plus the best solution that takes what time? Starts, exactly. So it's either going to be that right there, 1 plus the best of that, wherever the last class starts, or what's the alternative? Well, it's whatever the last event is. You skip. You're the very last event, event 2n, right? Either you take that last class and it's going to be, 1 plus that solution, or you just skip that last class and consider the previous event. You can make a notation up for start of I versus, start of the end of I, something like that. Once you get the basic idea, then we're not even going to use this as a solution. I just wanted to show that it could be solved by dynamic programming. Okay. So the dynamic programming solution, if you again start by considering this very last event, you're either going to take this last class or you're not. If you take this last class, then the max is going to be 1 plus the best schedule you have for the start. So this was event 2n. You need to have some proper notation for start and beginning, but let's not get too carried away with that because we're not going to follow this solution that much. It's just going to be the best for the period that's between 0 and the start of this event, right? So it's either going to be 1 plus the best of this, or it's just going to be the best of this event right here. This was event 2n minus 1. You could solve it this way, but there's a more intuitive way. So here's another way of thinking about it. Solution ij is going to be the maximal set of activities, period ij. So between some period, like this is I and this is j, okay? The most number of activities that you can put into that, we're going to call solution ij. And now here's so with that notation, our goal is to find solution 0 to n. And now this is the point that I want to make here. I'm going to claim that for any period, the first activity to finish is always part of the first to finish for every period is always part of the maximal solution for that period. Seems like an intuitive thing. Let's actually try to prove that the first to finish is always part of the best solution. Right? Once you know how to do this, once you know how to come up with the rule, first to finish is always part of the solution, and then argue that is true, then you know how to come up with greedy algorithms. So those are the steps for coming up with greedy algorithms. Understanding some rule, like first to finish is always part of the solution, and then knowing how to prove them. And so let's consider it in this particular case. So let's say, consider the optimal. So this F to F, that stands for first to finish. So let A star be the first to finish in the period ij. Okay. Furthermore, suppose that A star is not part of the solution. Of course, if it is part of the solution, then already our claim is true. But suppose it's not. This means that, so this right here is solution. And now, we don't even know this picture almost gives you the whole proof right there. So, we have some optimal solution. This is the optimal solution. We have some optimal solution. And we suppose that the first to finish, A star, is not part of this optimal solution. Perhaps there was some other value A that was part of that optimal solution. But we do know that A star is first to finish. A star is first to finish. And so the finish time of A star has to be less than the finish time of A. Just like this diagram shows. And this means that if we take solution and we remove A and we add A star, then that is also going to be optimal. In other words, if we just swap these two, we know that A star has to finish before A. And since the solution had no overlaps, that means A didn't have any overlaps. And so if we remove A and put in A star, that's not going to create any overlaps. Right? So what did the claim actually say? The claim said the first action to finish is always part of some solution. There can actually be more than one solution, but A star is going to be part of some solution. This is what's called an exchange argument. And is the basic flavor of all of the greedy algorithms we're going to talk about. All of the greedy algorithms are going to involve an exchange argument that allows us to say, already I know something about the solution. A star is part of it. Without knowing anything else, I know A star is part of it. Because if it wasn't part of the solution that you had, I could exchange some element of your solution with A star, and that would still be a good solution, the best solution. So let's take a look at how this algorithm actually plays out, and you'll maybe get a sense. So we look at the first activity to finish, and that happens to be this right here. It's not the first to start, notice, but it's the first one to finish. So we know that S1 is part of our solution. We circle it. And now we know that no other activity that overlaps with S1 can be part of our solution, because S1 is part of our solution, so nothing that overlaps with S1 can be part of it. So let's X out all of the things which overlap with S1, like all of those, for example, and we'll come to this problem. The problem that's left is in yellow. And now, this is just another situation. This is another time period, and we know that in this time period, the first to finish is part of an optimal solution, and so we select both of these. I guess green means go, so green was selected. This is the first to finish, so we take that, and we know that nothing that overlaps with this newly selected one can be part of the solution. So we remove anything which overlaps, the ones shown in blue, and we consider this smaller problem. And then you can basically see, through two more iterations, we basically have an optimal solution. This is a much simpler algorithm. It involves one pass through the sorted list. Everybody follow how that worked? Question in the back, Monica. That's right. In this situation, all we cared about was the most number of classes. That's right. So in the case that we wanted to maximize the utilization of the room instead of just the number of classes, then this approach wouldn't do it. Because then it's not clear. That rule that we're using, which is the first to finish, it's not clear you can exchange. If you had some optimal solution, it's not clear that just because I finish first, I can exchange with your optimal solution, and all of a sudden I'll still have the same amount of time. In particular, that exchange argument relies on the fact that we're optimizing only the number. Because I subtracted one from you. Let's say you had an optimal solution. I took the first one out and added mine in. And that preserved the number of classes, which we're max optimizing. And so that's why it works. So what I really like about your question is you can ask that question anytime you think a greedy algorithm is. So consider the proof that we just had. The proof ended with this line right here. And so now you can look at your question and say, if I was optimizing for actual time, would this statement be true? Not necessarily, and so it wouldn't exactly work for that measure. So I want to illustrate a second example of this type of greedy algorithm. It's slightly more subtle, requires a little bit more nuance, but it's the same technique. Question. What was the running time of this algorithm? It was linear. Because I have all of these elements in sorted order, right? They were given to me in sorted order. So I pluck the first one off. And now I scan through these right here, eliminate anything which overlaps with. The thing is, every time you remove one, you never have to look at it again. So, I believe what you do here is you start with the first one, you take this first one, and now you consider the second finishing time. If these two, if they overlap, then F2 can never be part of any optimal solution, so you junk it. If they don't overlap, then you take that one, because it's not going to conflict with the first one, and it is the first to finish in its period. Yeah, so the way I did the example, I sort of created this impression that you scan through all of them and remove them. But in implementation, you could be a little bit more clever about it. Okay, so let me set up the second problem. This is caching. So, how do I imagine my computer works? I imagine there's a nice green box, a nice red box, a nice gray box. One of them is called the CPU. It does instructions. It has some local cache on its chip. When it loads an address like A, it says, hey, what's A? And A either has that in its cache, or it doesn't have it. If it has it, it says, here it is. And of course, if it doesn't have it, then it goes to memory and comes back. And this is slow, and this is slower. Okay? Oops. Everything is slow if it's not on chip. This is slower and broken. Now, the question you face when you design a computer system is, what is the best way to manage your cache? It's a limited resource. You want to run your program quickly. How should you use that limited resource? So in particular, when some address comes in that you don't already have and you're full, which line do you evict? And many people make this decision in various ways, and various considerations come into effect. We're going to consider a very simple version of this. What's the best one can do? How do we even answer? What's the best one could achieve in a caching situation? Well, let's set up the problem so it's as easy as it can be. So, first assumption. How can we make the caching problem easy? Suppose we know the entire access sequence ahead of time. In other words, in our programming model, a program, when it loads, it tells us exactly what memory accesses it's ever going to want. And we, as the cache manager, get to decide on each access what to do. That would make the caching problem easy, or easier, right? In real life, you don't know what access a program is going to make. Second assumption, our cache is fully associative. What does that mean? What does fully associative mean? That's right. Any memory address can fill any slot of the cache. That's not how it works in real life. In real life, these rows are restricted to these rows, etc., in order to run quickly. But we're making the problem simple. So this is our problem statement. We have K, which is the cache size. And we have D1, D2, all the way up to Dn. This is RAM access. Our first n memory accesses are going to be, the first one is going to be at this address, then this address, etc., etc. What? The output is going to be the smallest number of cache misses. Least. This is the full problem statement. We have a cache size, and we're given a sequence of memory accesses. The cache is fully associative, What's the least number of cache misses? Question? Well, okay, good point. And you must implicitly, the way that you manage the cache must satisfy the request pattern. You know, it's not such a bad problem, right? You can think of libraries have this problem too. There's this huge off-storage site where all the books are really kept. And libraries, of course, have vans. That vans are fully associative caches because you can put any book at any spot in the van. And you have to minimize the number of trips you expect to make this based on the books that are going to be requested by the students in fall 2013 at Virginia, something like that. Not such a bad question to actually ask. Oh yeah, so contrast with the reality. I think I've said this before. I know that 2 slides from now someone's going to ask, well, this isn't exactly how my Intel Xeon E25760 works. You know, my line is cache, I have to bring in 8 at the same time, and plus it's, you know, not fully associative, blah, 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 blah. Yes, I understand this is not how your machine works, but this is still a good problem to solve because it introduces a new technique, and you can use this if you're actually doing research in this field. You might want to know what the best solution possible is, right? If you're given a particular memory access pattern, in real life, of course, you don't know that pattern ahead of time. But whatever cache algorithm that you're evaluating, you can use whatever this answer it comes out to be as a baseline for the best that you could get. Okay, so on to the actual solution. So this is known as this Bellotti eviction rule. You might have heard it in an architecture class that you've taken. But it's a very cool rule, and we're going to actually prove that it comes to an optimal solution. So here is the solution to this caching problem. It's called the Bellotti eviction rule, and it says if you must, it is what you would expect from a greedy algorithm. If your cache is full and you must evict an element, evict the element that you're going to access the farthest in the future. Remember, you see the access pattern that you're going to have. So whichever access is going to be farthest in the future, kick that one out first. Seems like an intuitive solution, but how would you argue that it's actually the best? So let me run through an example, just so that this pattern is actually clear. So suppose our cache begins with ABC, and this is our pattern right here. So clearly, ABC, these 3 are going to be satisfied just by the cache. But once we come to D, D is not in our cache. So which element should we evict? Well, A, we access immediately. B, we access right here. And C, we actually access right there. So by the Bellotti rule, we should evict C. And our cache will look like ABD. A and D are both going to be satisfied, but now it comes to time E. And so we look, A is accessed, D is accessed right here, B is the one that's accessed farthest in the future. And so we should evict B and put E in here. And similarly here, A, D, and E is accessed farthest in the future. So when we come to this B, we should get rid of E again. Ooh, sorry. There we go. Okay, so what was the point of this? We were able to satisfy this with 1, 2, 3, 4 cache misses. But here's a sequence. Here's a sequence that's not the Bellotti rule. See here, we didn't kick out B, we kicked out, we didn't kick out D, we kicked out B right here, which was not farthest in the future. But it also satisfied the sequence using only 4 misses. So with these type of problems, often there are more than one type of solution, but we know that at least the point of the greedy algorithm is that there exists some rule, like the Bellotti Rule, which gets us an optimal solution. The question is, how can we prove that our solution is actually optimal? How can we prove that the Bellotti Rule is going to end up with an optimal solution? Okay. So the surprising theorem we have about this, so I'm going to use SFF to be the Bellotti, so the surprising theorem is going to be that the Bellotti Rule is optimal. And in order to prove that theorem, I'm going to have to add a little bit of a few definitions. So a schedule for an access pattern is a sequence of either no op or evict x for y. So the schedule is essentially the schedule is what you do on your cache. So at every memory access, you either do nothing because your cache satisfies it, or you evict x for y. You evict some element x for some other element y. That's what a schedule is. And a reduced schedule is going to be a schedule in which a reduced schedule is one in which we only evict x for y when at that operation we're reading y. In other words, it's kind of like a lazy schedule. I know that all of you can finish your homework for today, but that's not a reduced schedule. Everybody's going to do it on Thursday night because it's due on Friday. So similarly, a reduced schedule is only going to evict x for y when at that time you need y. And notice a very nice observation is that the number of misses for a schedule, given any schedule, you can reduce it. You can reduce the schedule, i.e. move every time you evict, just move it until exactly the moment that you need that eviction. Otherwise, eliminate that eviction altogether. And you can only reduce the number of misses that you have. So any schedule you can transform into a reduced schedule and only reduce the number, possibly keep the same or reduce the number of misses. Why do we need to do this? Because we need to canonicalize. We need to start talking about optimal solutions for this caching problem. We don't really know how to argue about them, so we need to canonicalize how these operations are going to be scheduled. And so the way we're going to do it is to say you can assume without loss of generality that any schedule is going to be a reduced schedule because that by definition doesn't increase the number of misses. And now a reduced schedule we have some property that we can argue about. Okay. This is when the exchange lemma comes in. It's at this point. Suppose some reduced schedule S agrees with, so SFF, this is going to be the schedule induced by the Bellotti Rule. I call it FF because it's farthest in future. So SFF is the schedule that you get when you do the farthest in future rule. So suppose some reduced schedule S agrees with SFF for, this is what I said about this one being slightly more subtle. In the scheduling problem, the exchange rule was simple. The lemma that we proved was the first to finish is always part of an optimal solution. Here, we're being slightly more subtle. We're saying, if we have some reduced schedule that agrees with the farthest in future for the first j operations, then there exists another reduced schedule that agrees for j plus 1 operations and has the same or fewer misses. Why would we care about a lemma like this? Because it allows us to make the following type of argument. Imagine this is the optimal schedule. Well, we know that it agrees with SFF on at least the first 0. Okay? And without loss of generality, we can also assume it's reduced. So if we apply our lemma, that means that there exists... Let's apply our lemma. Where did our lemma go? If we apply our lemma once, what does that mean about S1? We apply our lemma once to the optimal solution. That's going to produce S1. And we know that now S1 has the same number of misses as the optimal solution, but it agrees with our farthest in future on the first operation. Now what do? We take our lemma. Our lemma says, give me a reduced schedule that agrees on the first j spots. I'll give you another one that agrees on j plus 1. So we apply it once, starting with 0, we get a schedule that agrees with our solution on the first spot. We apply it again, we get something which agrees on the second spot. We apply it n times, and all of a sudden we've turned any optimal solution to this problem into the one that we found. And moreover, throughout this exchange, the number of misses never went up. So does everyone at least see how we use this lemma? This lemma right here. It's always important to know why we prove things. This is what we want to prove. This is why we're proving it. Because once we have this tool, we can just apply it like a hammer, 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 and we show that the Bellotti Rule, farthest in future, the sequence that's defined by farthest in future, is actually an optimal one. All that remains is proving this theorem. I'm not going to do it because I'm out of time. I'll do that on Thursday. But I hope you can see that coming up with greedy algorithms much harder than prior techniques.